Alright, so today we'll be covering section 5.1, Introduction to Polynomials, Equations, and Graphs. So we talk about zeros of polynomials and solution of polynomial equations, graph factored polynomials, and solve polynomial inequalities. A monomial in x is an expression of the form where a times x to the n, where n is a whole number and a is any real number. The degree of the monomial is n and the coefficient is a. A polynomial is a monomial or algebraic sum and or difference of monomials. The degree of a polynomial is the largest degree of its terms. That's when you have it in a single variable. Polynomial functions. It is common to write a polynomial in the form of a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus, and then you have all your intermediate terms until you count down to 0, and you have a to the 0 and there is no x term. When n is a whole number and a to the n is not equal to 0. So this is just the generic form of any polynomial we write. It looks really intimidating, but it's just standing for some polynomial. We don't know where it starts, at what power. We'll just call it n. We don't know where it ends. We'll call it anywhere from here with the rest of the coefficients. Could have a constant term. The constant term could be 0. In this notation, a sub j is the coefficient of the jth term, x to the j. The degree of the polynomial is n. It's the largest number, largest power of x. A polynomial function is a function of the form of f of x equals a to the n, a sub n x to the n plus a sub n minus 1 x to the n minus 1, all your intermediate terms counting down to a sub 0, and where the first leading coefficient a sub n is not equal to 0. So once again, general form of a polynomial. Looks really messy, but it's just to hold a general spot, or just a placeholder for when we actually write the real polynomial that we're looking at. And then if we put an f of the x equals that, then it becomes a polynomial function. A polynomial equation in one variable, usually written in terms of x. It could be any other variable we choose, but x is typically what we write it in. Is an equation that can be written in the form of f of x equals 0, where f of x is a polynomial function. Note a review of Chapter 2 for techniques of solving polynomial equations, including factoring and quadratic formulas. So you want to go back through Chapter 2 to learn how to factor, to learn how to multiply binomials, trinomials together, things of that nature. Zeros of a polynomial. We say that the number k is called a zero of a function f of x if f of k equals 0. In other words, I plug in a number and that makes my entire function 0. This is also expressed by saying that k is a root or solution of the equation f of x equals 0. So if I were to solve for x, when I set it equal to 0, I would get a k back out. If f of x has a factor x minus k, then f of x has a 0 at k. In other words, if I factor it, break it up into parts, and one of those factors is x minus k. If k is a 0 of f of x, or in other words, if f of k equals 0, the graph of f of x will have an x-intercept at k, comma 0. So in other words, if I set this is my y value, remember this is my y value, if my y value equals 0, then this has to be my x-intercept. Verify that the given value of x is a 0 of the polynomial equation. So what we can do is, two ways we can do this. We can get everything on one side and then plug in the -3, or we can plug in the -3 and see if it makes the equation true. The quickest way would be plug into the -3 as the equation is written now. And so we'd have -4 times -3 squared minus 2 times -3 equals 2 times -3 to the third plus 24. And now that we have this, we're going to have -4 times 9, because that's -3 squared. Negative times negative is positive. Minus, and then that's -2 times -3, which is positive 6. And that's going to equal 2 times, and this is -3 to the third power, so we got Basically, it's 9 times negative 3 now, so that's negative 27 plus 24. So this becomes negative 36, because that's 9 times 4 times 9, plus 6 equals, and that's 2, that's going to be negative 54 plus 24, so that's going to be negative 30 equals negative 30. So that checks out. So yes, it does make, verify it is 0, yes. X equals negative 3 is a 0. There could be other zeros, but we check to make sure that it made the equation true, so we know that this one is a 0. To find the other zeros, we'd need other tools. We'll talk more about those later. Considering the two polynomials, the end behavior of a polynomial, consider the two polynomials, the functions f of x equals x to the fourth and g of x equals x to the fourth plus x to the third minus 7x squared minus x plus 6. So when we view the graph and we look close to the origin, they do not look much alike. There's some variations here. But when we zoom much further out, we can see that the graphs are very close together. So basically, if you zoom far enough out, if you have like 0 or 1 to plug in, if you plug in 1, can't see the scale of this, so small. You get 1 here, 1 here, 1, actually they get really close. But let's say you plug in 0 and you get 2 radically different values. But when you plug in something like thousands and thousands, like if you were plugging like, 1,000, well, 1,000 to the fourth plus, 1,000 to the third power. Well, that 1,000 third power is going to be really small compared to 1,000 to the fourth power. So basically 1,000 to the fourth power controls what the graph looks like. So if you zoom out, basically you're just looking at the first term of your polynomial if you zoom far enough out. What happens in the middle, not really concerned, but if you zoom far out, you'll basically be approaching whatever the leading term is and its coefficient. This suggests the following rule. The behavior as f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus all your intermediate terms all the way to a sub 0 is the same as the behavior of y equals a sub n x to the n when x is very large. Excuse me 1 minute. Sorry, somebody had asked me a question. To say that x is very large, we say that x approaches infinity if x is positive, and x goes to negative infinity if x is negative. If n is even, both ends will point the same direction, up to infinity. If a sub n is positive, and down to negative infinity if a n is negative. If n is odd, then the endpoints will point in opposite directions, down on the left and up on the right if a sub n is positive, up on the left and down on the right if a sub n is negative. So basically what's it saying? It's that if you have a sub n being positive, greater than 0, you're going to have, your graph is going to look like, and then something happens in the middle, and then it's going to go up. If a sub n is negative, then your graph is going to go something like, it's going to decrease, and then it's going to decrease some more. It's going to look something like that. And then something happens in the middle. When they're positive, a sub n is greater than 0. When it's even, you'll be going up on both ends. Something happens in the middle. When a sub n is negative, you're going to be opening down, and when something happens in the middle. If we have enough information now, we'll be able to sketch the graph of polynomials. To allow the following procedure may be helpful. Determine the x-intercepts by solving f of x equals 0. This is much easier if f of x is already factored. Determine the y-intercept by evaluating f of 0. Determine the end behavior and complete the sketch with the smooth curve. Alright, so we'll have our instructions. So sketch the following graph. So the first thing it wants us to do, it wants us to determine the x-intercepts by setting it equal to 0. So I'll set this equal to 0. So the first step, I'm going to say 0 equals negative x plus 1. So I got negative x times 2x plus 1 times x minus 5 quantity. And then I'm going to set each of these factors equal to 0. Negative x equals 0. It's already factored. Then I'm going to have 2x plus 1 equals 0. And then I'm going to have x minus 5 equals 0. And then once I have these, I'm going to get x can be 0, 2x can be negative 1, or x can be equal to negative 1/2. I'm going to have x equals 5. So now I've found all my x-intercepts. So my x-intercepts are going to be 0, 0. They're going to be negative 1/2, 0, and 5 and 0. So that's 3 points I have on my x-axis. Determine the y-intercept by evaluating, so second part, y-intercept is going to be if I plug in 0, so f of 0, and figure out what my values are. So I'm going to have 0 times negative 0, which is still 0. 2 times 0 plus 1 times 0 minus 5. Now we see this right here, we're multiplying by 0, so it's going to give 0 back out. So f of 0 equals 0, so 0, 0 is our y-intercept. And we could have seen that actually, we wrote the y-intercept right here, because we're only going to cross 0, 0 at the origin, so that's going to be our y-intercept as well, because we crossed the origin. To determine the end behavior, so we look at, if we were to multiply this out, what would be the biggest value? So if we multiplied this out, we'd have negative x times 2x, because that's our highest power, times x. And this would be the highest power term. Then we'd have plus all our other stuff down to our last terms. But right now, so we'd have this as being our greatest term, so we'd have negative 2x to the third plus all our other terms. So it's going to end behavior it looks like negative 2x to the third, y equals negative 2x to the third. So that means it's going to be odd. It's going to be negative, so it's going to look something like this. We're going to have the end behavior, dot, 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 and then it's going to go up. Whoops, that's incorrect. Did that backwards. It's going to look like this. So when we go to draw the graph, find something. Number 4, when we draw, I'm going to draw my x and y axis here. We'll have 1, 2, 3, 4, 5. 1. I'm going to go up. So where am I going to cross? My graph crosses at negative 1/2, 0, and 5. This is really close together. But anyway, so I'm going to start here. Start. And then I'm going to end down here. So this is just a rough sketch of what the graph starts. So I'm going to start at this end. I'm going to go through the x-axis here. I'm going to turn back. Whoops. Actually, I cross back out. And that's where I end. So I had to draw this a little bit smoother. Maybe draw this a bit bigger. Start, end. So I'm going to start in this quadrant, end in this quadrant. Then I'm going to have negative 1/2, 0, and then 5. And so I'm going to start over here, and I'm going to go down. I'm going to go through negative 1/2, turn back around, go through 0, 0, and then back down here. This is my negative 1/2, my 0. That's what my graph looks like. Now, you can graph a y-intercept too, but since our y-intercept was 0, 0, and that's our x-intercept there too, you don't see it crossing there. but those are our points of interest. Solving polynomial inequalities. When we worked with linear inequalities, we used the fact that polynomial functions cannot change between positive to negative without being zero in between. So for a polynomial function like f of x equals x squared minus 1, we know that f of x is negative when x equals 0. The only place where f of x equals 0 are when x equals plus or minus 1. Therefore, f is negative for every number in between negative 1 and 1. So basically it's saying if we want to have a graph, this is the x squared graph moved down 1 unit. If we have a nice continuous graph, what's going to happen here is if we cross the x-axis here, and we cross it here, we're going to have to be below the x-axis the entire time. Here we're above, we're below, and we're above again. Now later on we'll talk about situations, different situations, but we're not going to worry about that right now. Right now we're just going to be concerned with if we have zeros that only occur once. So when solving polynomial inequalities, we can use this to develop a procedure to solve our polynomial inequalities. We isolate the polynomial on one side of the inequality, solve f of x equals 0 to find the x-intercepts, choose a test point between each pair of intercepts, test each point to see where f of x is positive or negative where the interval it is in, and write your answer in interval notation. So, go for this one. So now we're going to have a polynomial inequality. So before, when we were graphing, we were just graphing, and those are the only solutions to points on those lines. Now we're going to be asking for all the values for where our graph is negative or where our graph is positive. It's like graphing linear inequalities, only with polynomial inequalities now. We're not going to get half planes as our solutions. We're going to get different areas. So what we want to do is first, instructions over here. So isolate the polynomial one side of the inequality. That is done. Solve for the x-intercepts. So find x-intercepts. So that means x plus 3 is equal to 0, or x minus 6 is equal to 0. So your x-intercepts turned out to be what? Negative 3, 0, and or 6, 0. Because if I plug in negative 3, it'll make this 0. If I plug in 6, it'll make this 0. Those are my x-intercepts. Next, choose a test point between each pair of points. So now I'm going to graph a number line. I'm going to plot off negative 3. I'm going to plot off 6. So I'm going to draw a line here and here. So this is my number line, right? And so I need to test each interval. So this is 4. So 4 test. So I have the interval between negative infinity all the way up to negative 3. So I'm going to test that interval. So if I were to test something in this interval, something like negative 4, if I test negative 4 into this inequality, I'll have negative 4 plus 3. Should have made this bigger. And negative 4 minus 6. And when I multiply this out, I'm going to get negative 1 times, and this is going to be negative 10. So that makes this positive overall. So positive, is that true? So this is no. This will be a positive number back out. So no, we don't want this interval. Over here, this interval right here, the easy number, this is going to be from negative 3 to 6 in this interval. And easy number to test in that interval would be 0. And so now we'd have 0 plus 3 times 0 minus 6. So that's going to be 3 times negative 6, which is going to be negative. So yes to this interval. And then we're going to test something between 6 and positive infinity. And when we test something like that, we test 7. So we're going to have 7 plus 3 times 7 minus 6. And that's going to give us 7, or actually 10, excuse me, positive 10 times 1, which is equal to a positive number. And so we want negative numbers, negative. And since we have negative, this is no. So the solution set we want is going to be right here. Now, we can include our endpoints, so we can actually say from negative and 3 all the way to 6, and we get to include our endpoints here. So this is our number 5. So we get to include our endpoints. We don't test our endpoints because they would make our equation true regardless of what interval we were in, which interval we thought we were in. And then it says it wants to verify our solution by graphing the polynomial. So we're actually going to graph this polynomial here. I'm going to mark off negative 3, negative 3 right here, and 6. And so if we graph this, sorry, children coming upstairs to bed. We have this graph, and we can see right here this interval right here will give us positive values of our, we're above the x-axis here, and we're above the x-axis here. Down here, we're below the x-axis. So since we're below the x-axis, we want all the numbers that are negative on this line or 0. So that means we want all the values that are going to be from in here to here. So that's from negative 3 to 6. Oops. My comma turned into a big blob. Alright, so here's what happens. The easiest way to do this is graphing these things on a number line because it's easier to check the intervals than graphing them on a graph. What Hawks will have you do is it'll have you sketch this graph, and then they'll have highlighted sections above or below the x-axis where you, after you hit your x-intercept, and so you'll click where you want your graph to be defined, and so you'll click this interval right here below the x-axis, and it'll highlight that interval as being part of your solution. And you won't click the other places. You'll say, I'm above, I'm below, I'm above, and I want the part below because I want to be less than 0. I want my part of my parabola that's going to be less than or equal to 0, which is from negative 3 to 6. Notice I don't care about the y values. I just want the fact that they are going to be negative. All right. So look at this one here. Our first steps have a little bit more work. We have to isolate. So I'm going to say that this is going to be x squared plus 6x plus 8 is greater than 0. And so I'm going to rewrite that as x times, and so I'm going to factor this really quick. X times x gives me x squared. 2 factors of 8 that give me 6. Well, 2 and 4. Right, because 2 times 4 is 8 and 2 plus 4 is 6. Apparently somebody is doing something strange outside. Apologize, can't edit that out. So now we're going to find our, so we've isolated, this is number 1. Next we're going to find our x-intercepts. I found that here, so part 2 x-intercepts, which is going to be x plus 2 equals 0, or x plus 4 equals 0, which is going to give us x-intercepts of x equals negative 2 or negative 4, or the points negative 4, 0, negative 2, 0. Now I'm going to draw my line. I'm going to mark off the points negative 4 and negative 2. And here I like to use dotted lines so they'll let me know that my endpoints can't be included. I use solid lines when I can possibly include my endpoints. Here I'm going to use dotted to show myself I can't use the endpoints. Doesn't really matter as long as you keep track of the sign. Make sure you get your numbers in the right order in number line. It's really easy to mix those up. So we'll have negative infinity to negative 4 is one of your intervals. Negative 4 to negative 2 is one of your intervals. And negative 2 to positive infinity is your other interval. Now that we have these, we need to test. Well, choose test points and test. So something left of negative 4 is negative 5. We plug in negative 5 and we get negative 5 plus 2 times negative 5 plus 4. Is that greater than 0? And so we're going to have negative 3 times negative 1, and that's going to give me positive 3. Is that greater than 0? Yes. I get positive numbers back out. Here I need to plug in something between negative 4 and negative 2. That would be negative 3 would be the natural choice there. There's an infinite number of numbers. You could choose negative 2.5. You could choose negative 3.5. We don't pick decimals unless we usually have to. Hold on one second. Apologize once again. It would be nicer if my kids were at school when I were making these. Unfortunately, it's the summer, and due to the current situation, I'm stuck with them for the rest of the summer. Anyway. All right, where were we? We were testing points. So we tested negative 5. We said it was yes. Now we're going to test negative 3 because that was the natural point between these two values. So we'd say negative 3 plus 2 times negative 3 plus 4. And we'd say, is that less than 0, or is that greater than 0? And we get negative 1 times, and this is going to be positive 1, which overall gives us negative 1, so that's going to be no. I get all negative values there. Then over here, something bigger than negative 2. Well, we could pick negative 1, but once again, 0, if it's in your interval, test it. It's a nice number. So we're going to have 0 plus 2, 0 plus 4 for 2 times 4, which is 8. That's greater than 0. I get positive numbers back out, so that's a yes here. So it looks like the intervals we want is we want the intervals from negative infinity all the way to negative 4. And I'm not going to include it because I'm strictly greater than, so I'm not going to include my endpoint. And then I want to union that with the other interval, which is going to be negative 2 to positive infinity. And so that's a, I'm not going to include that endpoint, so this is my solution, this is my number 5. So now if we look at this, and we want to graph this, so we want to verify by graphing. This is a parabola that's going to have zeros at negative 4, negative 2. And it opens up. 1, 2, 3, 4. 2, 3, 4. Whoops. Yep. Sorry. Negative 2. And so once we have that, we're going to open up here. So and so that's going to give us we're going to be positive right here, negative right here, and positive right here. We want where it's positive, so I'm going to want all this interval. So we I'd want all the intervals from here to here, negative infinity all the way to negative 4, and right below, and infinity all the way to negative 4, and, or negative 2 all the way to positive infinity. Oops. Positive infinity. So that's where our graph is positive, above the x-axis. Alright, we have our last example here, and this is nice, once again, because they've factored it for us, so it's really easy to find our x-intercepts. I'm sorry, I didn't realize I was so far from the mic. I apologize. And so now, for this one, everything's on one side. We've already factored it, so all we need to do is find our x-intercepts. So we're going to see negative x minus 2 equals 0, x plus 4 equals 0, and x minus 1, or sorry, 1 minus x equals 0. So that's going to give us our intercepts are going to be move the 2 to the other side, that's 2, 0. Move the 4 to the other side, that's going to be negative 4, 0. 0 being the y coordinate. And then this one might take a little manipulation, because if we'll say 1 equals x for this one right here. And so that means we're going to be between 1, 0. So there's our x-intercept. So now I'm going to draw a number line. I want to make sure I put all these x-intercepts in the right place. I'm going to have negative 4, and then I'm going to have 1, and then 2. When I'm using the number line method, I think it's easier just to evenly space everything, because you're going to be testing the intervals, and I like to test my points inside my intervals. I'm equal to I can let my values actually be equal, so I'm going to mark these with solid lines to know that I can be equal to 0. I'm going to include my endpoints. So now we're going to pick our test points. And so negative 5 would be a good one in this one, 0 in this one, and this is where you're going to have to pick a decimal, 1.5, and then something bigger than 2 would be 3. Now when testing these solutions, so we have the interval between negative infinity to negative 4, negative 4 to 1, and then 1 to 2. Remember, there's an infinite number of numbers between 1 and 2 you can check. 1.5 is just natural to come up with. 2 to positive infinity. So those are the 4 intervals we're looking at. Now when looking at this before, we figured out the numbers. We actually don't have to we don't need the numbers, we just need to know if it's positive or not. We could just keep track of the signs. So if I plug in negative 5 here, right? So I'm going to get negative 5, so that's going to be negative 5 minus 2, so that's going to be negative overall. Here if I get negative 5 plus 4, it's going to be negative again. And here if I get 1 minus a negative 5, that's going to make this positive. So let me write this out so we can see what happened. So here we have negative 5 minus 2, and then this is going to be negative 5 plus 4, and this is going to be 1 minus negative 5, which is plus 5. And so this is going to be a negative number, negative 7. This is going to be a negative number, negative 1, and this is going to be positive number, positive 6. When I multiply these numbers together, basically I'm just keeping track of the sign. I mean, negative times positive, which is going to give me a positive number overall. We want it to be positive, so this is positive. So yes. So notice how I did that very quickly. If I just look at the signs right here, and I'm not concerned with the actual values, then I can find my values very quickly. So let's try this for 0. So if I plug in 0 here, it's going to make it negative, positive, and then positive again. Overall gives me negative. I don't want negative numbers. We want it to be greater than 0. And here if I check this interval, and here's where it's really nice when it comes to decimals, because then you don't have to keep track of anything. 1.5 minus 2 is going to be negative. 1.5 plus 4 is going to be positive, and 1 minus 1.5 is going to be negative again. So that's going to give you positive. See yes here. And then here if we plug in 3, 3 minus 2 is going to be positive. 3 plus 3 is positive, and 1 minus 3 is negative. So here we have negative numbers. We don't want negative numbers. And so it looks like we want the intervals of negative infinity to negative 4, and we're not going to include the endpoints, and then 1 to 2, and we're not going to include the endpoints. So that's our solution. So for this, you can just keep track of whether it's negative or positive. You don't actually need the values. Now once again, what Hawks is going to have you do is they're going to have you graph this. So they're going to have you graph here. They're going to have your x-axis. They're going to plot off negative 4. They're going to plot off 1, plot off 2. And so what they're going to do is you're going to have these points, and then when you sketch the graph, that's 1, and that's 2, and they're going to say what's the end behavior. Well, the leading coefficient is going to be negative x to the third, and so we're going to start down here. We're going to end up, sorry, we're going to start up here. It's negative. You're going to have this sketch of a graph. That's your general graph shape. And you're going to say, okay, I'm going to divide it up into these intervals. And of these intervals, we want where it's positive. It's positive on this side, negative down here, positive up here, negative down here. So we're going to want the interval from negative infinity all the way up to 4, not including 4, and then 1 to 2, including everything in there. So that would be how you do it by graphing versus checking the intervals. And it's much nicer to check the intervals. It's a lot faster. You don't have to worry about graphing and make sure you start in the right place. It's taken care of by testing your intervals. And if you're going to test your intervals anyway, you might as well do it this way. But once again, Hawks is going to graph the formula for you. And once you graph the formula, it's going to say pick above or below the x-axis. You pick above here, below, above, and below. And then you say, where do you want it? You want it where it's positive. So you want this interval and that interval. And that's how you solve it in the software, courseware. All right. So I hope that was useful to you today. If there were very many interruptions, I'll have to go back and listen. Maybe I'll keep it. Maybe I'll record it, re-record it. But y'all have a great one. Bye.